Hello, physics students. Welcome to Newton's Second Law Lab Part 2, the effect of mass on acceleration. So at this point, you should have printed out the final two pages of this lab, pages 3 and 4, which are where you do your data collection and your data analysis. Pages 1 and 2 are instructions. Again, you're welcome to print them out if you want, but it's not necessary. So this lab is very similar to Newton's Second Law Part 1 in the equipment and some of the basic procedure, but it's actually very different in terms of its purpose and in terms of the big picture of how we manipulate the data. Because the purpose this time is to determine the effect of mass on acceleration. We know it's more mass is less acceleration, but we're going to prove it in an experiment. Just like before though, we've got to determine the mass of a system and the acceleration without ever using A equals F net over m. If we use that at any point in the gathering of our data, we're creating a circular argument. Just like in the last video I said I could prove the sky is pink if I could use that within my proof. So we cannot use A equals F net over m within our proof to prove it. So that means we have to determine the mass of the system. We're going to determine that with measuring an electronic balance. And then we're going to determine the acceleration from kinematics, not Newton's laws. We're going to use the motion detector and the TI calculator once again to measure the acceleration. Then we're going to see what happens in the universe with this system so that we could observe, measure, and figure out the pattern from just measured and observed quantities. So that's the goal. So again, as I said, the equipment is very similar. So you notice we've got the car and the track. Once again, we leveled the track so that it is tilted slightly downhill, so it's counteracting the force of friction in the wheels. So this rolls pretty close to constant velocity, neither speeding up nor slowing down, and we've counteracted friction with a little tilt of the hill. And then what we're going to do is we have to, as we're varying the mass and we measure the acceleration, we have to keep everything else constant. The big thing in that case is the force. Last time we varied force and measured A, and we had to keep the mass constant. This time we're going to vary mass, measure A, keeping the force constant. That's always what you have to do in an experiment. Keep everything constant so you are sure that what you're changing is actually the thing that's affecting the system. And keeping the force constant is very easy. All we have to do is hang one particular mass over the end of the pulley and keep it constant for the entire lab. This is what's going to be providing the force. So I put 50 grams, 50, hanging over the pulley. So, and then what I'm going to do is first measure the acceleration without any mass on the car. But the system still has mass. The mass of the system that's being accelerated is the mass of this. So let me go ahead and record that now. So I flip this over so it doesn't roll around, and I get the string and the mass on top. And my car is 308 grams right now, or my system, I should say, is 308 grams. Again, you're not going to jot 308 down. You're going to look in the Google Classroom stream and look in the Google Sheet or the image there, and you'll get the mass of your car. So here I jot it down. You will jot your own down. And once again, just like before, when I determined the mass, I had to convert it to kilograms. So 308 is 0.308 kilograms. There is the mass of the system. Okay, so next I'm going to set this up. I'm going to fire up my motion detector. So first thing, let's get the Lab Pro powered up. let it sing its little song. Oh, there we go, okay. I'll start up my little program here. It sings a little Beethoven for us, telling us it's up and ready. And there we are, it's up and ready. So now what I'm going to do is let this accelerate. And right now the mass of the system is 308 grams. So I'll fill that in my data table. I'll show you when I take the data, I'll show you a close-up of this. Okay, 308. Okay, so once again, I've got to catch this so that it doesn't fly off the end of the table and I don't break my car. But let's get the Lab Pro started. Okay. Okay, so let's wait for it to process the data. And we see here a nice little parabola. So again, this is a displacement versus time graph. When something accelerates, because of d equals 1/2 at squared, we see a parabola in the displacement graph. That doesn't help us figure out the acceleration because the slope of this graph, displacement versus time, gives us the velocity. So the slope at any one point velocity, we want the acceleration. So we've got to go to the velocity graph. Now, here you see the velocity increasing. That's when the car was accelerating. The slope of a velocity gives us acceleration, so we're going to use this program to curve fit to the first power, which basically gives us a slope of a straight line. The instruction says move the cursor to the start of the trend region. So I'm going to move in here. I would say the acceleration started there. Let me, I guess there's pretty good. And it ended there. So we're going to wait till that gives us the acceleration, the slope. All right, I don't know if you could see that. I see about 1.51, so I'm going to put that in for the acceleration. Okay, so this is what I see so far, what I have. So again, this was from the electronic balance, the mass of the system. You're not writing this down. You're going to look in the sheet that I have next to your name. It'll tell you your data, the mass of your system, which basically gets placed here. This is my acceleration, 1.51. Again, you're not writing this down. You're going to look up your data in the sheet that I put in the stream. So that was my first trial run. I got my mass and acceleration. Now what I need to do is make a change to the system and see how it responds so we could see the pattern that's in the universe, which we call Newton's second law. So I want to add mass to this. So what I'm going to do is I'm just going to take one of these aluminum bars, which is 250 grams, and I'm going to put it on top of my car. So then I'm going to take the mass of the old mass and I'm going to add the new mass, the additional mass of 250, and I'm going to enter that into my data table. And again, you'll see that closer when I show you the close-up view. I'm going to back this up and allow it to accelerate. And we should even observe with our eyes a slower acceleration, but of course this is going to measure for us exactly how much slower. Again, we need to give it some time to process the data. Nice parabola again, but again, we cannot get the acceleration from a displacement graph. We need a velocity graph, and we need to take the slope of the velocity graph to give us the acceleration. So we use the calculator to calculate that slope for us. I would say the beginning of the trend is there. The end is there. All right, it's calculating. All right, so I see 0.841, which I will just call 0.84. So again, this is my data. You're going to get your own, but what I did here, as you saw, I took 308 and I added 250 to it. That's how you get that number. convert to kilograms, measure the acceleration from the motion detector. Notice we have more mass, and indeed we saw less acceleration. More mass, less acceleration. That's the other part of Newton's second law. But of course, we're going to have more than just two pieces of data. We're going to see a trend, a graphical trend like before. So we're going to keep on increasing and see further decreasing. Okay, so let's move to the next trial. Okay, so we got our second acceleration. And again, we're going to keep going with that pattern, adding more mass and watching the acceleration get smaller, smaller, smaller every time, visually with our ears and with the data over here. So what I could do is now add another 250 grams to this car, okay? Add that to the existing mass, okay? And then put that into my data table, back this up. Okay, and get the motion detector going. Again, we're going to wait for it to process. Once again, we got a nice parabola, but that doesn't get us the acceleration. We need the velocity graph. The slope of a velocity gives us acceleration. Nice increasing trend there. We're going to get the calculator to calculate that slope for us. I'd say maybe starts right there, and the acceleration ends there. Let's give it a moment to process. I see a slope of 0.578, so let's call it 0.58. So I'm going to enter that right here in my data table, 0.58. Okay, again, oops. You can't see that. Okay, so again, this I added another 250 here. That's how I got this number. Converted to kilograms. Again, these are going to be your data assigned, or you're going to figure it out based on your assigned mass. And this, you're also going to get assigned your own acceleration. More mass, even less acceleration. Okay, so again, let's add more mass. Get ready for our measurement. Back this up. Start data collection. Okay, we're going to wait for the calculator to process. Another very beautiful parabola, but we need the velocity graph, so let's go look at that. Nice straight line. The thing is speeding up, accelerating. We need the slope of that. Let's calculate the slope. This line begins about there, so I move the cursor there. It ends about there, so right there. And let's give it a moment to calculate. I see about 0.449, so I'm going to call that 0.45. Again, we don't need any more precision because we're going to graph that, and the graph is already kind of a little on the crude side. Okay, time for some more mass. So once again, I'm going to take my old mass and add to it another 250 grams. Enter that into my data table. Back this up. And measure the acceleration again with a Lab Pro. Wait for it to process. Again, a great looking parabola, but again, we need the velocity graph. That's how we get the acceleration, slope of velocity. Nice straight line. So we're going to now calculate the acceleration by calculating the slope of that line. So we'll tell the calculator to begin calculating, say right around there, and stop there. It's going to calculate the slope of that. And I see about 0.365, so I'll call that 0.37. All right, so here is my data. Again, this is only a model because you're going to get your own value here by adding 250 grams every time to your original car mass, and you're going to get your own acceleration values. So again, keeps decreasing. Okay, now time for our last data trial. So what I'm going to do is add another 250 grams. Okay. I'm going to back this up. And now when I get this going, you're going to see with your own eyes how much slower it is. I added much more mass stacked onto the system, and more mass, less acceleration. You'll be able to see it with your own eyes, but of course, we'll see it with the numbers also. So let's go ahead and observe. Much slower. All right, another very nice looking parabola, but again, we don't need the displacement versus time. What we need is the velocity versus time. And we need the slope of this to give us, the slope of velocity time gives us the acceleration. So let's use the calculator to calculate that. I'll say maybe right around there is the beginning, and the end of the acceleration is right there. Let's give it a moment to calculate. And I see about 0.298, so let's call it 0.30. And there is the last entry in my data table. Again, keeps getting smaller. More mass, less acceleration. We are seeing the pattern, but of course we need to analyze it now graphically in more detail, more precision to get the true mathematical relationship. So let's move on to that. Okay, so we are now on step 14 of the data analysis. By the way, okay, so let's just read it. Calculate the force acting on the car from the 50 gram hanging over the pulley and record your answer in the data table. If you don't know how to do this, comb through your mechanics section of your reference table. I actually made a mistake. I put the mass of the car over here, and it doesn't belong here. So I apologize. Another mistake in this lab, okay? I guess I'm pretty consistent. I always make one mistake in the lab, so that doesn't go there. What I have to do is find the force on 50 grams hanging. And you may be wondering, well, how do I find the force of 50 grams? Again, you have to think, what's actually pulling our system forward? All right, this is hanging over the pulley, right? And then you let it go, right? Why did it go down? What was this mysterious force that pulled that 50 grams downward? So there's a word for that. We studied in our force unit 4 forces that we were calculating. Is it normal force? Is it spring force? There's 4 forces. Look back in your notes, look at your reference table. What is the force that makes that go down like that? That's what you have to calculate here. And just a reminder, this 50 is in grams. So first you have to convert it to some other unit. The 50 grams has to be converted, and ultimately you're going to get newtons over here, some number of newtons. So that's 14. Let's go on to 15. Calculate 1 divided by mass for each of the masses used in this lab. This is a little data analysis trick that you'll see later. It's kind of really a beautiful thing when you do this and you make a straight line out of a curve. But what you're going to do is you're going to take these numbers and just enter them on your calculator and do the reciprocal, like 1 divided by 0.308. Of course, you're going to have a different number here from your sheet, but I do that and I go 1 divided by 0.308 and I actually get 3.25. So I'll just fill that in here. Again, no units necessary because I have them all in the top here. They apply all the way down. And then I'll do 1 divided by 0.558. I get 1.79. 1 divided by, and you could be doing this along with your data, following me along with, of course, I'm going to have slightly different numbers. And then I'll do 1 divided by 1.058, and my entry is 0.95. To the hundredths place is just fine. 1 divided by 1.308, right? 1 divided by that gives me 0.76. And then 1 divided by the last entry, I get 0.64. So that's how you fill in that column. Pretty simple, just punching numbers on your calculator. Okay, so now we are on to step 16. Plot the acceleration versus mass, kilogram data on the axes provided. Mass is on the bottom axis, so obviously acceleration's on the side, and then sketch a best fit. Notice this is bold in italics, a curve. It's not going to be a straight line. So what I'm going to do is I'll pause this now, and then I'll just show you my graph. So rather than you watching, because you have your own data graph. So let's take a look at what my data looks like. So you see my points plotted. By the way, I left all these labels off because I didn't want to do all the work for you, take all the fun away from the lab for you. I wanted you to have a little fun plotting these axes, right? And then plotting the points. Don't forget, you've got to have something here, and something here, right? So don't forget those unless you want to lose some points. So that's the trend. But then, as it said, sketch the a best fit curve, and you get 1 point for that. So just some kind of curve that goes through here. Obviously, you know, a straight line doesn't work. You see those points of curves. So you could connect the dots, but, you know, kind of extend it beyond also and just draw a smooth curve in. All right, so that's that graph. Moving on to 17 and 18 right here, we've got create a new graph plotting 1 over m data on the x-axis and the acceleration on the y-axis. And here's how you're going to be graded for those points. For that, now you're going to take, we just plotted this column and this column, right? Those two columns. And now we're going to plot this on the x-axis, all of these, and this on the y-axis. Okay, so those two are going to be plotted right here. Okay, right here. So let me pause. I'll plot the data, and then I'll show you what I have. And of course, you plot with your data, and then I'll explain how to analyze from there. Okay, so here are my points. Again, I left the axes labels off. I didn't scale these. Well, I did, but I didn't show you how I did that. I also didn't put any labels. That's all for you to do with your own data. But notice we do have a linear trend. No matter how you scale these, if you scale them properly and proportionally, you will see a rising line like that. That's the interesting thing when you plot 1 over mass over here and acceleration here. And by the way, the labels you could just take right off your data table here. So 1 over mass, 1 over kilograms goes there, and acceleration and the units there, and then think of some kind of title that applies. So now we're going to step 18, draw best fit line, and then 19, we're going to calculate the slope of that best fit line. As usual, I recommend dotting these with a little bit of ink so that when you try again and again to draw a best fit line, you know, you don't have to worry about losing all your points and having to replot. So let me get a ruler. Again, this is a bit tricky for me because I'm trying to squeeze my way in front of the camera without nudging the camera's tripod. But basically, it's something like, you know, and you could make it go through the origin too, because that's definitely what would happen in a graph like this. And maybe something like this. You want to have it pass through the center of the trend. Oh, I didn't realize there were 2 points up there. So I shouldn't have done that so hard because now it won't erase nicely. But see how I did that? And the points are still there. Well, the ink is not so good. Let's darken them a little bit. Maybe this is an erasable pen. I don't know, but okay. Let's try something like that. I guess that's good. See, these two are above, closer than the one out here, so it is kind of like an average, okay? So I do that best fit line, and now 19, I have to calculate the slope. So what I'm going to do is say slope. To keep it simple, I'm just going to say change in y over change in x. Remember, you need a formula always for all calculations on the Regents when you're showing a calculation like this. So then what I'm going to do for my graph, oh, I don't even remember how I scaled this. Okay, so that was all the way up here. Well, I'm kind of giving you the answer now, I guess. 2 meters per second squared was the height of this, minus 0 meters per second squared. Okay, so that's this value and that value, you know, subtracted. And then this way, I'm starting between 0 and what was this? I would say maybe like 3.9. Okay, so 3.9 is the final. 1 over kilograms minus 0, 1 over kilogram. Okay. So then I calculate, again, this is, you're going to have different numbers, right? So this is my data, but I'm just showing you the pattern, what you do. And I get 0.513. Maybe I'll, yeah, 5.1. And then my units, again, if you're confused about units, just leave them all. I've got meters per second squared in the top and 1 over kilograms down here. Okay, and there it is. The slope equals that value. You're going to have your own, so, but that's how you do it. Okay, so now we're on to step 20. Once again, we've got to figure out where m belongs in Newton's second law and to what power based on our graphs. So number 20 says, inspect your acceleration versus mass graph. Explain how the curve demonstrates that m belongs in the denominator of Newton's second law and not the numerator. In answering the question, explain also what the graph would look like if m was in the numerator instead. So what I mean by that is, just like in the first law, we've got to think about patterns, mathematical patterns. So if I had a graph, a function like this, okay, y equals x over 1. Plot that on a calculator. See what shape you've got. Then plot y equals 1 over x. Plot that on a calculator. See what shape you've got. Now look at your acceleration versus mass, and which one of these does it look like? If it looks like this one, then x belongs in the numerator. If it looks like this one, then x belongs in the denominator. And that's how you answer that question. You say, it belongs in this place because, you know, that's what the graph looks like. If it were in the other place, the graph would look like this, which is not what we see. So you have to have 2 sentences here to explain number 20 over here. Okay, so I think I need to move this down like this. And yeah, that would be number 20. Okay, number 21. the tricky part. So you've demonstrated with your data that m belongs in the denominator of Newton's second law. Now you will use your graph to determine the force accelerating the system. To do this, assume that A equals F over m. Using only your slope and this equation to guide your reasoning, determine the force on the car system, the string mass, and the masses you used in your lab. Somehow the slope is related to force. So I've got this value. And how does that relate to force? Well, notice I've got meters per second squared in the top and 1 over kilograms in the bottom. Meters per second squared is acceleration. This is 1 over mass. So what I have is the slope equaling this. Slope equals acceleration on top and then 1 over mass on the bottom. How does this relate to force? Well, from Newton's second law, A equals F over m. If you solve for force, force equals m times A. So how does this relate to this? Now, this can be altered. If I had this, I had, let's say, 10 divided by 1/2. You do that on a calculator, you get 20. You punch it in 10 divided by 0.5. But another way to do it besides doing it on a calculator is to realize that when you divide by a fraction, it's the same as multiplying by the fraction flipped over. So knowing that with numbers, do that with variables. Try and simplify this by taking this out of the denominator. See what you get and see how it compares to MA. M times A is the force. See if you could simplify this to figure out how this relates to force in newtons. There's your hint, okay? So go ahead and try and figure that out from this. So, okay? All right, well, you're then going to calculate, so that all goes, that calculation, by the way, or I should say the answer, the solution goes right here. Okay. 22. Calculate the percent error between the force you calculated here in step 14, right here, all the way at the beginning. Okay, I guess you can't see that right there. Okay. And the force you calculated here in 21. Okay, so that's what you do right here, percent error. 23. Answer the following. Did the lab prove A equals F? This is basically like the same as the conclusion in the last lab. It's going to be 4 sentences. Let's read along. Answer the following. Did the lab prove A equals F net over M? Hint, no it didn't. Explain why it didn't. So you say right there, no it didn't. Explain why it didn't. And then here's another hint. 2 things affect the acceleration according to Newton's second law. Look at the equation if you're not sure. What are they and how do they affect the acceleration according to the theory? So look back at the equation. What are those 2 things? When one goes up, what happens to acceleration? When the other one goes up, what happens to the acceleration? So there's two statements. Which of these relationships did this experiment prove and which did it not prove? 4 statements, okay? So that's Newton's second law, lab part 2, the effect of mass on acceleration. I hope you enjoyed the lab as much as I did. I'll see you next time.